Okay, let's see. Right here. Okay, so your last test, which is a programming test number 3, it will be tomorrow, Friday. You can please check the guide about any policy. It should be just consistent with the previous 2 tests. Should be no surprise. The practice test has been released. Also, the solution has been released. And it will be also beneficial to also redo lab number 4 and also practice test number 2. Just try to practice before the actual test. And your lab number 5, so please make sure you study the background material about abstract classes and interfaces and make sure you kind of know them before the exam day. They will be covered. And also the priority should be lab number 4 to really go over the solution, right? So for tomorrow. Right, any questions? Anything that's not clear about what's going to happen for the course? Okay. One of your fellow students asked me right before I started recording about if you really want to get started about studying for the exam, what should you do? I will maybe talk about it very briefly, okay, right now. Just give you some idea, but I will maybe give you any additional information, if any, maybe next Tuesday as well. So we still got 1 class next Tuesday. So we're going to cover recursion today and also next Tuesday. I will also need to point out to you guys about certain materials you definitely should really go over as well. The recursion that we're going to cover in this course is rather basic, but there will be a certain pattern you will actually have to try to do practice before the actual exam. So you got maybe about more than 2 weeks to really get this understood and also practiced. Well, I'll give you all the resources. As for the exam, so the exam is actually going to be, of course, paper and pen. It's going to be a written test, basically, but it's going to be paper. So you go to the designated classroom, and then I believe it's, I forgot exactly the room, but please check, right? Just go to the room, and then we'll give you the paper and some answer booklet. I'll talk more about specifics of the exam next Tuesday in the last class. Okay, it's going to be a written test, and primarily written, like a short answer. So short answer. And of course, here the short answer can be maybe you got to write some Java code, not to the extent that you have to program in the programming test, but you may have to write some Java fragment. So there will be some code, and there will be some explanation or justification. I'll just say explanation in general. All right. And then, how should you study? Okay. Usually, well, always, I try to make up the exam question just based on what I teach in the class. So what I will do is I'll go over the slides. Also, I go over the iPad notes to see what has been covered, and any insights I also mention or discuss with you guys, in the class. So those are the materials where I'm going to make the questions from. So your safest bet is to really go over just the materials that we cover. So you should really go over, I would say iPad notes might be the most important one. Okay, because there are many things that we kind of go over in detail step by step, and also there were many insights also documented there, right? And if there's any part you're not exactly sure how to clarify, well, you cannot really clarify by yourself. You can feel free to check the lecture recording. Are you supposed to rewatch all the recordings? No, I don't think so. It's actually quite many, right? So the recordings are really there just for you to check certain parts on demand. You're not really supposed to go over the whole course. It's going to be too time consuming. I don't think that'll be the most the most wise use of your time. Okay, definitely iPad notes, and then also the slides and any written notes that I put on the lecture slides. So there were some written notes about typecasting. There were some written notes which I'm going to show to you about recursion. So these are some example notes you really also go over as well. I think they complement quite nicely to our lecture materials. And also any example code that we also made available to you, right? Okay. So these are the stuff. And then as we try to cover more recursion today and also Tuesday, I will also give you a little bit more hints about what you should really study for the recursion as well. But I'll also point out to you all the resources. I already posted them earlier this morning. All right. So I think that's really what you should do, right? So to really get started on the studying. Of course, form some study mates, study group, and chat with your fellow students. I'll try to also announce maybe some extra office hour maybe after the last day of the class. I still need to confirm with you about the time, so just bear with me. I'll make sure I do that. And as I said, I also try to make some Zoom hours available, just in case you don't want to commute to this campus outside the last class, which is okay. I'll try. Okay. All right, any questions? Okay, we're good? So the materials I actually posted online about the recursion, I'll get to them once we get to the recursion part, which will be very soon. So I'm having some trouble connecting to the Wi-Fi, maybe just my machine. So I think I'm currently just using my mobile data, so maybe it's not very nice to really use the iClicker today. So today, there's no attendance check, but I'm pretty sure you will stay, right, for the material. All right, we're gonna talk about some exciting stuff, okay? But we're gonna take a break for sure, as usual. All right, let's recap very quickly, all right? So last time, we basically tried to synthesize all the stuff that we learned so far about inheritance, right? So this page over here really tried to combine a number of slides really from your like a polymorphic method parameter topic in the lecture, right? So what you really want to take a look, I'll just summarize quickly the question you want to ask yourself. Number 1, 2, 3, and 4, do they compile or they do not compile? Justify that. And also, if they do not compile, why adding some typecast is going to make it compile? Second question. Third question is, if they compile and we try to execute it at a runtime, what's going to happen? Either the class cast exception might occur or it does not occur. That's also something you want to know pretty well. So we got 1, 2, 3, 4 different cases. I think these 4 cases illustrate quite nicely about compilation versus runtime class cast exception, right? You think about different possibility. I think I discussed these 4 examples thoroughly on Tuesday, so please check the recording if necessary as you study through the example. All right? And then this page here also is very important. We talk about polymorphic collection. Of course, in this case, the collection we talk about is array. Basically, we're saying that if you look at the array here, okay, that's the only thing I want to talk about. If you look at this array here at a compile time and also runtime. At a compile time, we declare the array statically. Every element in the array should have the static type students, right? So every element has the same static type, never changes. However, dynamically, you can see at index 0, we have the dynamic type, not students, but resident students. At index 1, we have the dynamic type, non-resident student. Also, again, not students. However, they are not really random classes. Both of them, the dynamic types, must be able to fulfill the expectation of the static type, meaning that both of them are the descendant classes of the static type, right? That's really the essence about polymorphism that's going to apply to the collection context. So that's really something you want to study for. You want to start from studying about how the students over here, based on the parameter static type, why can we be so tolerant about adding different dynamic types at the runtime? That's number 1, which we explain. And number 2, when you actually try to call this expression here, okay, there's a loop. So we basically go over the students array index by index using the loop counter. Can be 0, can be 1, can be 2, and etc. And then we're calling the same method get tuition. And in our student management system example, there are 3 different versions of get tuition. Either the base amount using the premium rates or using the discount rate, right? These are the 3 different versions. But exactly which version should be called depends on what the dynamic type is for this particular context object, which we explain. So for example, for the very first iteration, the context object has a dynamic type resident students. In that case, call that version using premium rates. In the second iteration, the dynamic type is non-resident students. In that case, call another version using discount rate, right? So that's something you also need to know how to trace. Okay, I'll leave also the details to you. The final one that we talked about was the polymorphic return types. So you want to look at any accessor whose return type is actually not primitive. Let's say it's a reference type. And this reference type happened to be somewhere in some inheritance hierarchy. So students happen to be the top of that student management system hierarchy. So we're saying that given that static type is students, dynamically, again, similar, dynamically, it can be any of the descendant classes of students, meaning that any class that can fulfill the expectation of students, you may return that as a dynamic type. All right, so what you want to look at is exactly how this line over here can actually return to you dynamically different type at the runtime, depending on what I is. For example, when I is equal to 0, it's going to return resident students. When I is equal to 1, it's going to return non-resident students. Right? So once you get the return type, return value back, you can also try to invoke different methods, and also dynamic binding is going to make sure the version that's being called depends on whether the dynamic type is this or this. Right? That's also something we discussed in detail. Please take a look on the discussion from last time. But maybe go over the slides first. If you need any further clarification, you can look at the recording. Okay. Any questions about this? Okay. All right, and then we spoke about the overridden method overriding in the inheritance. We just use the equals method. So the conclusion is, whenever you're trying to find out which should be the version of method to be called, the idea will be you want to find out the closest ancestor that has the overridden version. Okay, so for example, let's say in this case, you can see along the ancestor path, the default equals that's from objects is never overridden. So the only version you can call will be in the object class. That's the most straightforward one. Okay, a little bit like a point v1 case. And then for this one here, this is another extreme. So dynamic type is actually C, and that class already overrides the equals method. In that way, remember a class is simply its ancestor. In that way, the closest ancestor that has the overridden equals is just C itself. So that's why we call it C version. Another here, let's say C here does not really have the overridden method, the overridden equals. So we search upwards. So now B being the parents, they do have the equals method. So we just choose that one. It's the closest one. What about this one here? Let's say we got equals here, and also we got equals here. That means C over here in its ancestor, we got version 1, version 2. Well, you can think about objects like another version, because object is also the ancestor for any class. So we got 1, 2, and 3 versions. So now which version should we choose? The principle is the closest ancestor. Right? Think about you're always searching upwards along the ancestor path of the dynamic type. In which case, once you find the closest one, you stop searching. All right? So in this case, it will be this version being called. Right, so this is only about, of course, the principle is about finding the closest ancestor, but the example itself just about equals method. But it should be applicable to all other scenarios about overriding. Overriding is very common when you have inheritance. All right, any questions from last time? Okay. The last part I want to talk about inheritance is just a single slide about a table. Okay, I'll just talk about it very quickly. So if you go to slide 90 of your inheritance lecture, right? So there is a table over here. I would just want to speak about it very quickly. So this table here summarizes about the typical scenarios where you have to determine whether or not some expression in Java or in OOP in general should really compile. So this table here is, when we say type checking, you're checking to see if the types are being used correctly. Basically, that's what type checking really means. It's something that many compilers for any OOP is simply just doing, but they're just doing that automatically for you. But as we study through the foundation, we should know how to type check them, at least the ones I'm mentioning over here. I'll show you how you can read them. Okay, let's just take one of them as an example. Right. So here, let's say we have this one here. Okay, let's say this one. Okay. If you look at this expression here, this expression here has actually two parts, as you can see, right? First of all, it's a variable assignment. And then it also involves a typecast. So there are two parts over here you gotta worry about, right? So let's now try to highlight the two parts. Part number one is about the typecast. And part number two is about the variable assignments over here. So now you got to discuss them separately or in the right sequence about which, in order for this variable assignment to really compile, what will be the conditions that should be satisfied, right? So the exact conditions is mentioned over here, but I'll just talk about it since I think that's something we also mentioned earlier in the lecture. Okay, how about the blue part over here? So this is about typecast. How can we make a typecast compile? Either upward or downward, right? Okay, so that one there, basically you're basically asking, so C, the cast type, must be either the ancestor or descendants of the static type for Y, right? So this should be either upward or downward cast. Okay, in order for just the right-hand side of the variable assignment to compile. Okay, assuming that it compiles. In that way, the right-hand side over here would have the static type C, which corresponds to the cast type, right? So now in this case, you can think about the left-hand side over here has the static type C. And now if we bring this into the context of this variable assignments, how can we make this variable assignment compile? So the static type over here on the right-hand side must be able to fulfill the expectation of the left-hand side static type, right? So you want to think about if, let's say, this X over here has certain static type. Let me just say T, for example, right? Static type. So now we got to make sure C over here must be able to fulfill the expectation on T. That means C must be a descendant class of T, right? So these are two conditions that's actually important. So this is a completely valid exam question, not necessarily something directly from the table, but if I give you some line over there, I'll simply ask you, in order for this particular line to compile, what would be the conditions that should be satisfied? Or in order for that not to be compiled, what would be the condition it can be violated, right? If they are really equal questions there. So I just talk about one of the cases. You can definitely speak, look through the simpler ones, and also this is slightly more complicated, right? But there's also something we spoke about, like the the page that we spoke about. I'll show to you. So this last row in the table somehow is relevant to this example here. You will see, right? Once you study for that, right? All right. So you want to be able to actually work on the inheritance, not just at a very concrete example level, but also you also want to be able to generalize it using some abstract symbols. So that's really the value of this particular table. All right. All right, any questions about this table here? Okay. All right, so that's about everything I want to cover for inheritance. And you guys can definitely start going over all the slides, all the materials about inheritance. Okay. If no further questions, let's now talk about some new lecture. That'll be the last topic for the course. That'll be recursion. We wouldn't cover something very, very advanced, not really. So in this course, we just want to give you some introduction and being able to somehow link the tracing about recursion, for example, into the stack that we spoke about earlier. When we first introduced stack, that's when we talk about how you can trace the chain of method calls, right? When we talk about exceptions. So I want to revisit the idea about stack, because when you first want to understand how the recursion works, stack is actually very fundamental to really make that understanding happen. That's something we'll do today. And I'll also assign some exercise for you. I'll also give you the solution video to also go through. All right, that's about recursion. Okay. And before I start, so for the do I have that slides? Just give me one moment. Yes, we do. Okay. So we're going to learn about how to solve the problems recursively. I'm first going to talk about just at the conceptual level. Doesn't matter how advanced the recursion problem might be. Could be at the 2030 level, or could be at the 2101 level data structure, or even the more advanced level in 3101, the algorithm course. Is the recursion problem are going to be solved fundamentally similarly. You just need to know the principles, and then it's just a matter of how many problems you can manage solving. So whenever you see a similar problem, you can solve it right away. But if you encounter some problem you haven't ever seen before, you're just going to be creative about coming up with the solution, right? It's quite true in CS or in engineering in general. All right, and then we're going to look at some examples. So today I'll give you some example on the screen, maybe just one example. I'll give you some exercises. We can still go over solution next Tuesday. I also want to start you with about how to run recursion on the array. So that's definitely something that's more important to really understand, right, out of these two lectures. All right, and then more advanced example, We'll see. Okay. If no, you can also see the example exam question, which I also make available to you before Tuesday. Right. We'll see. And then I talk about this right away. Recursion is, there's no way to learn about recursion or master recursion. I mean, when I say master, I really mean to really master it just by taking 2030 or taking 2101. It's more like an ongoing learning process. I just want to give you some ideas about the extra resources you should really think about. Okay? So coding bet will be immediately relevant to you guys for the exam, especially for coding bet recursion 1. So this will be, there will be collection of problems that your exam might test you on. Not exactly the same, but similar level of difficulty. So I would suggest once we speak about some example today, the slides are also there on the lecture side. You should really study ahead. Try to keep solving problem. That'll be the best way to get prepared for the exam. And recursion number 2 is not really something we'll get into for this course, but I'm listing over here just so that if you want to get a little bit more advanced exposure to it, you can also feel free to do that. Okay? Recursion is not useful just for this course. It's actually very useful in general. And what's really the best way? My personal view is to really master recursion, you will have to learn a so-called functional programming language. Because in this language here, you just have to define almost everything recursively. So that'll be really the best way. It's definitely beyond the scope of this course, but for those of you who might actually want to really master recursion or just to get better understanding, you really want to learn another language on your own. This has functional language is not usually covered in our curriculum, unfortunately. So you will have to take some initiative to really sharpen the knowledge, okay, about recursion. Right? I included some example here. Haskell is actually quite a industrial strength functional language that you can actually invest your time on. Right? It's kind of worth your time. For those of you who might be interested in discussing with me about Haskell, I'll be more than happy to. I did program in that before a bit, so you can, I'll be happy to discuss with you about Haskell. Right? So some tips over here. And then if you look at the lecture sites, right, I'll just point to you about the links I just made available earlier this morning. Okay, you will see that. So now we got the slides, and also we got some required reading. So this document here summarizes about all the problems we're going to talk about in the lecture slides. And that one kind of show to you how the pattern of solving problems recursively can be applied to each one of them. So you will see, it's a good summary just to see how to understand the basics. And then I talk about coding bad over here, right? Just one, just for exam, just one, not two. And there is a past lab from the earlier 2030, and you can also give it a try. I include both the starter code and also the solution. So I would suggest give it a try. You know, it can definitely help. And what we're going to get into will be something about Fibonacci number, just as a basic example for recursion, but there will be some assigned exercise to see how we can trace the Fibonacci sequence using a stack. That one there is quite a bit of tedious example to do, but it's actually very important to get right. So I also recorded some tutorial video for that. You can also take a look. Try to trace that by yourself first, and then compare that with the solution. Okay. And then example code about the different recursion problem that we're going to talk about in the class is already there. And also, if you want to look at some extra recursion problem, there's also some tutorial session there, right? You can also plan your time on that, right? So these are all the good resources, you know, for you. So I think just choose the one you find necessary, okay? Okay, so let's now dive into the contents. Okay, recursion, what's the principle, right? Go for a little bit bullet points, and then I will also try to visualize the principle here. Okay, recursion is useful in expressing solution to problems that can be recursively defined. Recursively defined simply means if I want to define a problem recursively, that means the definition itself contains the problem itself. It sounds a bit weird, but we'll see, okay? So the recursion also has quite a nice connection to the mathematical induction that you guys did, maybe in the high school, maybe in the earlier courses, right, in the math. So base cases simply means the simple ones that you can solve right away. You don't need to even think about much, just solve them, okay? Also, we got something called recursive cases. In that case, we cannot really solve the problem right away. What we got to do is, number one, we got to assume the sub-problems can somehow be magically solved. Assume that we got solution. And then you're going to somehow combine the various solutions together, and then somehow magically you can come up with the right solution. I'll visualize that to you. But that's basically intuitively what that really means. One thing that beginner about recursion really find weird is, how can I simply assume things will just work on a smaller scale if I want to solve something bigger? Actually, there's no magic here. So the best way to really convince you is we're going to look at some tracing about recursion. Okay, that's something we'll do. Okay, recursive cases, and then we'll get in there. So you can also study the bullet points later. And similar to mathematical induction, right? If you want to prove something, you got to solve some individual values and assume by making the inductive hypothesis, and then use the inductive hypothesis to show something bigger will always work. Something like that, right? So if you want, you can also maybe go back to your math course and look at how the mathematical induction work. Weak induction should be enough to really also draw some connection. Okay. All right, let's now talk about visually how recursion can be understood. Oh, sorry, wrong side. Okay, there we go. There we go. Okay, for now, I'll just minimize this. Okay, there we go. Okay, for solving problems recursively, base case. So case number one would be we simply got simple ones. Base cases. So base cases simply means we're given a very small problem, and we can solve it directly by supplying its solution. Right? So the color convention is blue means the problem, green means the solution. All right? If I'm given some small problem, I can supply its simple solution right away. Case number one. You definitely need base cases to make sure your recursive solution can terminate. Okay? I'll just mention something here, which we'll also see. Base cases ensure termination. Otherwise, you might run into infinite recursion. And another case, which we call a recursive case. So recursive cases. Okay, that's another one. So what it says is we are given some much bigger problem. You can see this is much bigger than the smaller problem, right? We just cannot solve this right away. What we do is something called divide and conquer. Divide and conquer. Okay, I might be spelling that wrong, but anyway, divide and conquer. But that means to overcome. So given some big problem here, what we do is we divide the big problem into strictly smaller sub-problems. All right, so you can think about each one of these is a strictly smaller problem. So this is important to annotate. So this is a strictly smaller problem. You can divide the original problem into as many sub-problems as you like, as long as each sub-problem is strictly smaller than the original one. Okay. And here comes the critical part. Once you define the strictly smaller sub-problems, you can assume for each one of them, they simply got their corresponding solution. So this solution here, we assume it exists for this sub-problem. This solution here, we assume it exists for this sub-problem here, and etc. So now we got solutions, but we got multiple solutions. But what we really want is a single solution for this original big problem. What should we do? So somehow we can combine all the individual sub-problem solutions into the bigger solution. So that's the conquer part. All right? Divide part simply just go from, you can think about this part over here is about divide. Okay? And then once you actually got individual ones over here, got individual ones over here, you will try to conquer. Okay, divide into different sub-problems right here. Okay, That's really the principle. And then we're going to see over and over, this pattern here will just be repeated when we are solving the problem. Okay, so let's now see some Java code just to give you some idea quickly, and then we'll look at an example. Okay, so let's say this is a Java method, and this method here is recursive because you can see in order to implement m, and we're given, let's say, some integer I somehow tells you about certain input, right? Like a parameter, like an input. And we're saying that in order to implement n given I, we're going to somehow solve it using n, the same method, but given a different input right here, right? First of all, this here, m here, and m here, these are the same method, right? If you're calling a method inside its definition or inside its implementation, it's so-called a recursive call. That means in order to solve n, I want to solve itself, right? It sounds a bit weird, but that's really the way to go, right? In order to solve n on I can now try to solve n on j instead, but it's still going to work somehow, all right? And what's really important is you want to make sure that, so I here and also j here, they are in some way more like the size of the problem. So this will be the size of the problem, and this will be the size of some subproblem. And remember we said earlier, so think about I here, conceptually, is more like the size of the original problem. And the j over here is like the size of the individual, strictly smaller problem. So conceptually, what will be the mathematical relation we are expecting, right? So in order to make sure the recursion is actually valid, otherwise you'll run into some infinite recursion, as we'll see, okay? So now think about this one here. I want to make sure j here is a strictly smaller problem. So that means j should be strictly less than I. We'll see this kind of pattern very soon, all right? Of course, here I'm not telling you exactly what m is trying to do. I just say conceptually, right? Whenever you see a method try to call itself, it's a recursive call. You got to make sure the recursive call will always give you something that is conceptually strictly smaller. Otherwise, you're going to run into trouble. Okay. Okay. Let's now take a look at some example before we take a break. There will be one slide there, just review the concept about a stack, which I wouldn't repeat. We already talked about what a stack is, right? About pushing and popping or adding and removing when we talk about method called execution. This is something I will definitely do today when I trace some recursive call together with you. So I'll review all the terminology. But that's something I want you to go over on your own as well. That's something we covered already. Right? It will be slide number 5, right? Just about the basics about how a stack can work. Okay? That's something I'll leave to you. And then let's now talk about the typical hello world recursion problem. All right? Factorial. Right? I'm pretty sure you guys know what a factorial is, right? Okay? Let's dive directly into it. Okay? I got a definition for you already. Okay? So we got n factorial and, if you remember, exclamation mark, right? Factorial. Good. So now we got two definitions here. We say that if you can think about n here is the size of the problem, n here. The problem is about calculating factorial, and n here is about the size, how large of the factorial you want to calculate. You may want to calculate factorial of 1,000, you may want to calculate factorial of 2, right? So that's the size of the problem. So first of all, let's clarify. This is the size of the problem, which may be very, very small, so you can solve it right away, or which may be not small anymore, that you cannot solve right away. Okay? So we say that this one here, well, okay, it's the size of the problem. So the definition is, if n is equal to 0, 0 factorial by definition is simply just 1. And then we say that if n is not equal to 0, that means we may have 1 factorial, 2 factorial, 3 factorial, etc. This will be the definition right here. Okay? It's going to be n multiply n minus 1 multiply n minus 2 all the way multiply to 1. That's the definition when n is larger than 1. So a very simple question to ask. Is this definition here recursive? Is this definition or solution, right, to factorial recursive? All right, that's the first question. Is it recursive? What would make a solution or definition recursive? You should refer to itself, right? And the problem we are trying to solve is explanation mark. Do you see any explanation mark here? We don't. So it's not recursive. As simple as that. All right? Okay, I'll write it down. Yeah. So over here, this is not. Oh, actually, you know what? Since we're asked the question here, I'll say right here, the answer. No. Because the explanation mark does not appear. In the definition or solution. A recursive definition for factorial should be, in order to do n factorial, somehow we want to calculate the factorial of something strictly smaller. That's something we can expect to see in order to have a recursive definition. But this one here is not recursive. It's a valid definition, I'm just saying it's not recursive. Okay? Now, what would be a recursive definition? All right, so that's a question, right? Let's now try to just give you another alternative definition. Okay, I'm going to put it here. So now, alternative solution. That is recursive. And if we want to design the solution for some problem recursively, let's think about two cases. Base case, recursive case. Right? Base case might be the one to maybe think about first. What would be the smallest problem we can dream about and solve it right away? Okay? So we're trying to still solve n factorial. You can see this part here is just the same. That's the same problem we're trying to solve. Okay? And now we talk about base cases. Equals, okay, two cases. First of all, we got base cases. We can say if n equals 0. Oh, by the way, guys, so here 0 is a mathematical equality. It doesn't mean variable assignment. Right? We're still talking about math. But when we translate the recursive definition to Java later, we can worry about the equal. Okay? So this is something we call base case. If the problem size is simply 0 factorial, we can solve it right away just by returning something. And that one there, just 1. Otherwise, if n is, you can say, strictly larger than 0 or larger than equal to 1, doesn't matter. Okay? If that's the case, we're going to solve the problem recursively. Recursive case. To resolve that recursively, we have to give a strictly smaller problem. All right? So this means, okay, I'll write it down directly. We can say n here, which is given, multiply n minus 1 factorial. This is the recursive definition because you can now see that we have factorial over here and we got factorial here. And we are saying that in order for you to solve the factorial of size n, you can simply try to assume we got the solution to a strictly smaller problem of n minus 1. Whatever that solution is, you can multiply that by just n. And somehow it will just work. To really see how that works, we have to trace some code. That's something we'll see. All right? So this means it's recursive. So this part here tells you that's a recursive call. Just a recursive definition. Recursive definition or recursive call. All right, any question here? We're good? Okay. If it is good, let's now, okay. Let's talk about some Java quickly. So you can translate this recursive definition into Java, right? Let me just go over the code with you very quickly, and then we'll take a very short break, and then we'll do tracing right after the break. So the recursive definition we have, right? Factorial and also factorial. You can see that we got size n, but here we got strictly smaller, which is n-1, right? That's kind of fits nicely into our pattern. And let's look at Java very quickly. I'm defining some method, factorial, integer n. And then I want to return integer. So I just declare some result. Okay? Eventually, I want to return the result. If n here is simply 0, small enough for me to solve right away, I just assign result equals 1. Otherwise, if n is not equal to 0, that means the problem for now is too large for me to solve right away. In that case, we're going to somehow assume we got the solution here. We can write it out directly. But this n-1 here represents a strictly smaller problem. And whatever solution it might be, multiply that by n, which corresponds to the current problem we are trying to solve. So what you want to notice is, in order to solve the problem of size n, we have to somehow use the solution to a problem of size n-1, which is strictly smaller. All right? That will be your first recursion example, okay, in Java. Okay? So any questions about this Java code here? Very simple, but I think this will be maybe the only time I'm going to use a call stack just to show to you how you're supposed to trace the stack using a stack. But there are two ways of tracing recursion, which I'll also speak about as well. All right? So why don't we take a very short break? Okay? So today, no attendance check. All right? But just take a break. All right? So let's now trace this factorial problem. Right? It's a rather simple one, but you will see that even that one, you can already see in order to do the tracing manually, you got to be very focused and very careful, right? I'll try to do that together with you for the simple ones. And then I'm going to talk about another recursive problem after this, Fibonacci number. That one there, I'll assign some exercise for you, but I would suggest you also try on your own. You really want to know how to do things, systematically. All right? So there are two ways to really trace recursion. So we can definitely see how to do it on a stack, and factorial, and also the also Fibonacci sequence example will be the only two we're going to show to you how to use call stack. Of course, you can use call stack to trace every recursive solution. That's not a problem. However, that might turn out to be too low level as we get more advanced. Once you get more advanced, you want to be able to think more creatively about recursion. In that way, using a call stack is not a way to think. There's just some fundamental you have to know, but once you pass the beginner stage, very soon, we're going to use another way. Let me start with another way. Okay, that might feel a little bit more intuitive to you. That one there is using more like a tree. Remember, the only tree we have seen so far is like a smartphone or student management system example, right? So now we're going to use a tree, right? Very naturally. Let's say we want to see exactly how factorial 3 is calculated, right? I'll put it here. So we start with factorial 3. This is our problem. Right? Of course, you can think about factorial number 3. When we want to calculate it, we're going to put that onto the stack, right? That's the starting point. But let's not worry about stack just yet. In order for me to calculate factorial 3, is 3 qualify as a base case? Not really, because only 0 should be qualified, right? So that means we're going to calculate factorial 3 as 3 multiply factorial of 3 minus 1, right? Good. Hopefully that's not too fast. So 3 multiply factorial 2. 2 is 3 minus 1, right? And this is another thing for us to worry about. So now, is 2 qualify as a base case? No. So further. So the tree can just grow deeper and deeper. 2 multiply factorial of 2 minus 1. 1. Now, is 1 qualify as base case? Still no. All right. So what we're going to do is this one here and this one here is going to be 1 multiply factorial 0. And factorial 0 is indeed a base case right here. And that one there is just going to be 1. So once you kind of reach the base case, you somehow have to have a systematic way to go back to all the call that have been suspended and fill out the result. So you can calculate the overall result. So let me just highlight certain parts over here. I'm going to also use the same color for other for the stack tracing. Let's say for this part here, green. For this part here, pink. And this part here, blue. And for this part here, 3. All right, just a little bit easier for us. Okay, so now this factorial 0 is 1. That's being returned. So we know that this here, conceptually, is simply 1. And factorial 1 is going to be 1 times 1, which will be 1. So you can also think about this value here is replaced by just 1. And then factorial 2 is 2 times 1, which is 2. Right? So that means this part here is 2. And factorial 3 is 3 times 2, which will be 6. So the overall result is going to be 6. But in order to calculate that, you will need to solve some intermediate, strictly smaller problem along the way. Okay? So you can see by defining something here as a program, things will just work like this way. So that will be the most difficult part as a beginner for recursion. Because when you actually try to think about recursive solution, you don't really necessarily want to think about how exactly to trace it. Instead, you want to think more about how you can define the original problem by some strictly smaller problem. And then from there, you can use some tracing to verify your solution. That'll be the way to go. But it really takes some experience. It's easier to say than to do. I totally understand. It takes some time. Right? That's why I gave so many resources to you. So you should definitely dive into recursion right away after today with the different problems. All right. All right, let's now use a call stack to trace very quickly, right, to see how things go, right? So what we do is, let's say we got factorial number 3, right? That's what we want to trace. So what we do is, we're going to put factorial 3 onto the stack. That will be the starting point. Over here. Okay, we know that for factorial 3, when we calculate it, so n will just be 3 over here. We know that it's not a base case, so this is what we're going to execute, this branch. So that one is going to be 3 times factorial, I'll just say fact, just easier, right? Factorial of 3 minus 1, which will be 2. So what's going to happen is, okay, this is what the execution of this is going to trigger, right? But this one here is going to, so this one here is going to be suspended because we got another method call to the same method, right? That's a recursive call. So what should we do? We should really put this one here onto the stack, all right? So for that one there, I'm just going to highlight it as factorial 2, which will be blue right here, all right? So I'll put factorial 2 and put it onto the stack right here. Finally, sorry, not finally, ultimately, we want to calculate factorial 3. Before that, we had to calculate factorial 2, and etc. Okay? So now for this one here, how should we do? We should really execute this method here with the input value 2. And 2 is not a base case, it's going to go here, right? It's going to boil down into 2 times factorial 2 minus 1, which would be 1, right here, right? And that one there tells us we still have to suspend the call of this because there's another method call here, factorial 1, right? Factorial 1 is right here, okay? I'm going to push the method call here, factorial 1, into the stack again. So I'm going to get factorial 1 right here. And that one there is going to be factorial 1. All right, so far so good. And for this factorial 1, we are going to execute it the same method here, third time. So n will now be just 1. Still not the base case, right? So that means it will boil down into 1 multiply factorial 1 minus 1, 0. All right. And we still have to suspend this because we've got factorial 0. Okay? Factorial 0 is going to be green. Over here. Oh, maybe not that green. There we go. Factorial 0. And then I'm going to put factorial 0 right here. Right? That's the green one right here. And we're going to execute the same method for the 4th time right here. So now we got 0. Now it is qualified as a base case, right? So that means we're going to execute this branch over here. Result will just be 1, and it's going to be returned. So that would mean this part here is going to be 1. And it will be removed from the stack because it returned. So you can think about this one here is actually 1 right here. After we have removed factorial 0, what will be the next method to execute? Factorial 1, right? The top of the stack. And in order to execute this one here, right? That one there is going to be 1 multiply factorial 0, which we know that has returned 1 right here, right? So 1 times 1 is going to give us 1. So this value 1 over here tells us we're going to return 1 from this factorial 1. After it's returned, we remove it from the stack. Right? Once we remove it from the stack, what will be the next method to execute? Factorial 2, right? That will be the top of the stack. And then to really resume the execution here, it's going to be 2 times whatever that's returned from factorial 1, which is 1. We just calculate it, right? Just go all the way from bottom up. So here it's going to be, this part here is going to be 1. So we got 2 times 1, which will be 2, right here. All right, so that means factorial 2, we can also return the value 2. All right, so once you got 2, it's removed from the stack. The final thing that will be on top of the stack will be factorial 3. So keep going. So now, to resume its execution, it's going to be 3 times whatever factorial 2 return, which we know it returns 2. All right, so this part here, it returns 2. So we actually got here 3 times 2, which will be 6. That tells us this will be the final method to really execute, right? 3 times 2. So this will be the final value to return. This will be the final value to return. And that's it. In some way, the factorial tracing is not too bad. You just got to be very careful about which one should be added to the stack and which one should be removed. Basically, there's only one recursive call here, factorial, okay, which is not difficult to really trace. But if you like, you can feel free to try maybe factorial 4, just an exercise, just to see how you can make it a little bit bigger, how you can trace it accordingly. Right? So this is something I hope at least you can get some idea. Okay? Let me recap. Given a piece of recursive solution in Java or any OOP, or actually any programming language that will support any function call method call, you can do recursion. Okay? You can either try to trace at a high level like this, which is something you want to get into ultimately when you get more advanced, or using a call stack to understand the fundamental. But the second example about recursion, we're actually going to see to really trace that one, it's going to be much trickier because rather than having a single recursive call, we got multiple recursive call. In order to trace it, it requires more care about how you do things. But that one there, I'll leave as exercise. There's also a detailed solution video to walk you through. That one is a highly recommended exercise to do. Okay? Any question about factorial? All good? Yes. So me for factorial? Yeah, I would say factorial, since we already did factorial 3, right? You can maybe try factorial maybe 4. That one should be rather easy to do. Just do in a very similar. That one is a different one. That's the Fibonacci number, which I haven't got into just yet. I want to give you some look ahead, really. Yeah. Okay, we'll get there. Okay. All right, good. Before we talk about Fibonacci sequence, some common error just about recursion, right? Since we just learned about factorial. Let's see this. Well, I already tell you this definition here is problematic. What's wrong with this? No base case, obviously, right? It is nicely tell you that to solve n, we can assume we got n minus 1. But there's no base case. What's wrong with that? First of all, no base case. It is wrong because in order, let's say we calculate factorial 2, make it even simpler, right? To calculate factorial 2 is going to boil down into 2 times factorial 1, which boil down into 1 times factorial 0. Would it stop? Not really. Which boil down into 0 times factorial minus 1, and etc. It will never stop. There's no base case. The base case from before, say, if n reaches 0, you gotta somehow assign the result to some definitive value and return it. But now, without a base case like that, you just keep going. You're gonna get some stack overflow exception in Eclipse. It's an infinite recursion, right? So it's an infinite recursion. All right, that's a common mistake. You got to make sure you always include at least one base case. That's why I said in the beginning, base case is really to ensure your code that's done recursively will terminates. Okay, another error. How about this one here? I do have a base case. What's wrong? That's subtracting 1 or more at the conceptual level to really solve a problem of size 1. Right? So to really solve a problem of size 1, I am trying to assume I got that solution right away. That's not right. Remember the pattern? We're going to assume that we got the solution to some strictly smaller problem. Right? So this is not a strictly smaller problem. And let's just trace a little bit, right? This one here, we got factorial 2. Let's say we start with that. 2 is now qualified as a base case. So that one there, according to definition, is going to be 2 times factorial 2. And then factorial 2 is going to be 2 times factorial 2, and etc. So you never get a chance to really reduce the problem size down to the base case. So having a base case here is actually useless because you will never be able to get there, right? So the reason we want to have some strictly smaller problem along the way is because ultimately we want to reach the base case so we can start returning, or we want to start popping from the stack so we can actually return, right? So that's another insight you want to keep in mind, all right? This is another infinite recursion. All right, that's good. All right, let's now do another one here. Okay, second example, Fibonacci number. Okay, maybe you have seen that before, I hope. If not, that's okay. I can just briefly talk about it. Basically, for Fibonacci sequence of Fibonacci number. So sequence is simply called capital F, right? The first two numbers are always the same. We say that this is the first number in the Fibonacci sequence, and this is the second number in the Fibonacci sequence. They are always just 1, 1 and 1. And then, starting from there, the third number, the fourth number, the fifth number, etc. They follow the following definition. If I want to know, for example, let's say if I got certain parts in the sequence, now I'm here, I want to know what should be this number here, all right? The idea would be you want to get what is the previous two numbers in the Fibonacci sequence, and then you simply add them up together, conceptually. Okay, for example, let's verify. What would be the 2 over here is simply the addition of the previous two numbers, 1 plus 1. And 21 over here is simply the addition of the previous two numbers, 8 plus 13. right? So now, based on that, guys, what should be the next number here? Huh? Just tell me how to calculate it. That'll be easier. 55 plus 89, right? And whatever number it is, and then so on. All right? That's a Fibonacci sequence. And now, let me just give you another one here. For example, if I want to calculate, for example, Fibonacci 4, right? The fourth number. By definition, I need to find out the previous two numbers, which will be 3 and 2. Fibonacci 2 plus Fibonacci 3. And we know that Fibonacci 2 over here, by definition, is just 1. But Fibonacci 3 here, we got to further divide that, which will be Fibonacci 1 plus Fibonacci 2. Right? And then now, both of them are defined, 1 and 1. That's just visualizing the definition. Of course, this can go on. If you can definitely try to draw something similar, maybe for Fibonacci 5. That can be some example for you, right? Exercise. All right, so now we want to give a recursive definition for a Fibonacci sequence. So once we're done with the recursive definition, I'll show you very quickly the Java code, and then there will be one tracing exercise for you, which I will give you the solution, right? Give it a try. All right, so we can say Fn here, okay? It's a little bit like an n factorial, right? The same way, right? N factorial. N here is the size of the problem, depending on which number you want to find out, right? This will be, so now, different cases. How many base cases do we have? 2. 2, all right? Because this is a base case, this is also a base case, right? If you want to find out F1, F2, you just get 1, all right? So you can say 1 if n is equal to 1. Also 1 if n is equal to 2, right? Base cases. Okay. So think about these two are base cases, which you can compute right away or return right away. Base cases. And then anybody would like to try. How do we define the recursive case? In general, recursive cases could be multiple. It doesn't really mean you always have just one recursive case, but I can tell you that for Fibonacci sequence, one recursive case should be enough, like a factorial. If I say n is larger than or equal to 3, now what should I do? So somehow, in order for that to be recursive, I should really mention f again, the same problem. However, I shouldn't say f of n. That's a common error, right? I cannot really just mention the same problem of the same size. It should be a strictly smaller size. Hopefully that's enough hints for you. What should I write here? F of, yeah, Ibrahim, go ahead. Yeah, exactly, very good, yeah. But the order doesn't really matter, right? Okay, good, awesome. Yeah, so I can say f n minus 1 plus f, oh, I can move that a little bit. N minus 2. All right. So you can think about this is a recursive call. This is just another recursive call. 2 recursive calls. All right. Are we good? Okay. So that's the recursive definition. And I'll show you the Java code very quickly. So Java code looks like this. So we got f of n. Oh, sorry, that's a recursive definition. So I don't need to repeat. So let's say we got Fibonacci number, right? N here. If n is equal to 1, result will be 1. If n is equal to 2, result will be 2. Will be also 1, beg your pardon. And then otherwise, if neither 1 or 2, it's going to be Fibonacci is a recursive call, but n minus 1, right? Also Fibonacci, they're calling the same method, but n minus 2. That's it. Now, the challenge is trace Fibonacci 4. I would suggest when you trace this one here, do some pre-processing. try to draw some, I drew, oh, actually this one is already here, right? So this one will be useful. So take a look at this tree over here and make sure you understand how that was derived. And then, as I trace through along the way with you in the tutorial video, try to maybe try to do that by yourself first before you look at the video to compare. All right, and try this one here. It's going to be very useful, I guarantee. All right. All right, any question about this? The solution video is already on the lecture site. Please take a look. All right. All right, good. So guys, we got about 12 minutes or so. I can maybe work on some string recursion problem together with you. But before that, there's one slide I want you to study, all right, for preparation of Tuesday, right? I want to mention that very quickly, okay? So factorial and also Fibonacci is done, all right? And I think the slides I also show you Fibonacci 5. You can also try that one as well, right, for tracing. That will be the much more challenging one. You can also give it a try. Okay, we're going to talk about string in just one moment, okay? But I want to mention a very specific slide number I want you to go over before Tuesday, okay? Okay, good. So I want you to take a look at slide number 20, okay? 20 over here. Slide 20 over here is something that you can expect on the exam, this kind of problem type. Basically, we're saying that in order to run recursion on an array, so there are two ways for you to think about how to create a strictly smaller problem. Either you try to create new arrays along the way. Let's say I got an array of size 10. To really create a strictly smaller problem, let's say of size 9, do I just create a new array of size 9? Or there is a better way to do it, right? So the first bullet point here is really about just creating a new array objects along the way. Conceptually, it's okay, but it's just a waste of time and space. So what I want you to really make sure you understand before Tuesday, I will still go over and visualize it, is about second bullet point. We are trying to use the idea about call by value. This is the third time we are talking about call by value. You can see how useful it is, call by value. By using the call by value, we're basically introducing two integer parameters that will be passed along the way for every recursive call. So this is something I want you to study very carefully before Tuesday. It's going to help you a lot. All right, that's something, please do the assigned study before Tuesday, right? And then after that, we're actually going to solve two recursive problems on the array. And if you go to the coding back, it's also there. Okay, 10 minutes. Let's now solve some recursion problem on strings. All right. Before that, okay, I can move directly to iPad here. Let me talk about, I think we can solve at least one. Okay, today. But before that, I need to help you understand one of the methods that you might want to use. Okay, so let's start with, so this is string tester, just to show to you how to use the certain methods there. I think this code is also on the lecture site. So let's say we got a string, ABCD. So string is like an array of characters. All right, so you can think about this string over here, ABCD. So A is at index 0, index 1, index 2, index 3, right? So you can think about S over here is simply something like that. So 1, 2, 3, 0, 1, 2, 3, and we just say A, B, C, D. For those of you who took or is taking 2031, you will know this very well, right? A string is an array character. An array of characters, okay? And you can check to see whether or not the string is empty. That's easy, right? Apparently S is not empty. And also you can use substring, okay? That's the method I want to talk about, all right? A little bit tricky, but it's not too bad. So let's say if I say S star substring I and J. All right. I and j are simply some integers. For example, it could be 0, 0, 0, 4, 1, 3, 0, 2, right? Just integers, nothing negative. So what this will do is, okay, let's now see what this will do in general. So this is going to form a substring, just another string, by collecting characters in this interval. So maybe in your math course, you learn about closed interval and open interval, right? So this will be I and j. So this is a closed interval, and this is the open interval. What does this mean? Okay, just for... So this means we're going to collect all the characters at index I plus 1, all the way to, not including j minus 1. I is included, but j is not included. So you can rewrite it in a different way. So this will be as if we got I, also j minus 1, but this one being closed. All right, it's a precise definition for substring. All right. There will be some special case. So ij over here, typically, okay, how about this? For the substring not to be empty, I should be less than or equal to j. It should be. If it's the opposite, if I is larger than j, then it's empty. I'll show you. All right. So for example, let's see over here. Okay, 0, 0. What does that mean? All right, so this one here, if you think about the closed interval, so this will be as if we have 0 minus 1. So this is the case where you can think about this is I, this is j. So I is strictly larger than j. So this is special case. Whenever you're passing a substring interval like this, that means you only return an empty substring. Okay, so it's just going to return an empty string. You can also give it a try. Okay, now how about this one here? 0, 4. What's going to be the substring if I got 0, 4? Anyone? It's basically 0 to 3. Yes, I agree. Absolutely. What's the substring? 0, 1, 2, 3. The entire string. Right? A, B, C, D. Right? So from 0 to 3. 0 to 3. And this 3 over here just happen to be the length of the string. Oh, beg your pardon. I really meant to write here. The 4 over here just happen to be the length of the string. Accordingly, the 3 over here is the index of the last character. Right? That's something you can think about. All right, let's do another one. What about over here, 1 and 3? That means it should be 1 to 2, right? 3 minus 1, right? So now, what should be the substring? 1 and 2, B, C. All right? So that one there should be B, C. All right, so play with the substring. Maybe when I recap about the substring, maybe on Tuesday, I can give you another mathematical property to think about. All right, I'll do that later. There's another method, which is called a character at. That one there, like array indexing. I just want to return the character at index I. So if I say character at maybe 1 over here, for example, is going to return character B. Right? As simple as that. Of course, the argument you put must be a valid index, like a valid index for the array. Otherwise, you're going to get things like array index out of bound exception, something like that. All right? So these are the methods you should really know in order to do recursion. All right? I got 3 minutes. Okay? We can at least talk about some idea. The first one. Okay? At least we can do one. Palindrome is a typical one. Do you know what a palindrome is? That means a string that reads Forward and backward, just the same. For example, race car, is it a palindrome? Yeah, because read it forward, backward. R-A-C-E-C-A-R, right? The same. So this is a palindrome. Is this a palindrome? Not really. But if you read it forward, A-R, whatever, backwards, S-R, already not the same, right? So this is not a palindrome. And is this a palindrome? R-A-C, R-A-C, E-A, A-E, not the same, right? So this is not a palindrome. All right? Let's talk just about the idea about what a palindrome is, right? So if you read forward and backward, of course, to determine if your string is a palindrome, you can simply run a loop to say, I will go from left to right, and then I'll go from right to left, using maybe loops to see if they match the character. That's one way to do by using a loop. It's an iterative solution. How can we solve this recursively? That's the question, right? Let me talk about the idea, and then we can see the Java code very quickly, right? And then there will be another 2 problems you can think about. I can still talk about them very quickly on Tuesday, right? At least we'll do one problem. I'll give you some visual hints. Somehow, we're going to solve this problem recursively like that. Think it this way. If you're reading it forward, the first character you're going to read will be R. If you read it backwards, the first character you read should be R as well, right? So now, this one and this one here should match. If R and R match, does it guarantee it's a palindrome? Not necessarily, it might be, but no guarantee. So that means we still have to look at this strictly smaller problem that's highlighted as pink to see if there's a palindrome. And go forward. Give me 1 minute or 2, okay? And here, we try to look at A and S. This is already not matching. Can it be a palindrome? No. So we return false right away. And for this one here, R and R match. So we go on to look at whether or not this middle string here is palindrome. So we look at strictly smaller problem. A and A match, so there's a possibility. So now we look at the middle part, CEA. So CEA over here. And now we look at C and also A. Are they matching? Not really. So there's no way it's a palindrome. So what does that really mean? So this means, okay, I'll write down something here. Whether or not something is palindrome. A string. Okay? Now, conceptually, what should we do? Take the first character and take the last character. If they match, we have a chance. Okay? Compare the first and last characters. If match, then you have to run some recursive call. You're going to say if it's palindrome, somehow you have to somehow put some substring. And the substring is actually going to get rid of the first and last character. So that's a strictly smaller problem that's being passed to the recursive call. All right? If they do not match, just return false. If not match, simply return false. That's the conceptual idea. Of course, you also got to think about what the base case is. For example, empty string. Is empty string a palindrome? No, it should be, right? Empty string, if you read it forward and backward, just empty. So it is a palindrome. How about a single character, A? Is A a palindrome? Yes, A and A. Read the same, right? So these are the possible base cases. Conceptually, I just described to you how to really think about this recursively, right? You want to take the first and last character first, compare them, and then recursively find out, if necessary, if the middle part is also palindrome, and then somehow combine the result together. So take a look at the Java code that's on the slides for palindrome, and then I'll also talk about these two, but study ahead. about this recursion. Get used to the recursive thinking and look at the resources on the lecture site. All right? I'll see you tomorrow in the test.